Okay, let's jump right into this explainer. We're going to talk about something we all share, those fundamental chemistry rules you were basically forced to memorize back in school. You know exactly the ones I mean, right? The absolute laws written up on the chalkboard that we all just blindly accepted as the absolute gospel truth. We scribbled them in our notebooks, we regurgitated them onto our exams, and, well, we never really gave them a second thought. But today, we're going to look a little closer at those supposedly unbreakable foundational principles. So here's a provocative question for you. Is your chemistry textbook lying to you? Now, I know, lying sounds a little dramatic, doesn't it? But stick with me here, because over the next few minutes, we're going to uncover two major foundational misconceptions that are honestly still presented as absolute facts in practically every high school classroom around the world. Get ready to unlearn a few things.
Section 1. Breaking the octet rule. The 8-electron myth.
Okay, so let's define the rule exactly as it was hammered into our heads. The octet rule is the principle that all atoms want exactly 8 electrons in their outer shell. We were taught this as if it were a universal law of nature, right? We just completely bought into the idea that elements like carbon, nitrogen, and oxygen inherently just want 8 electrons to be happy and stable. It was the ultimate rule of thumb. But what actually happens when we test this rigid rule against physical reality? Well, let's take a look. Think about our first mystery compound here, boron trifluoride, or BF3. It's just one central boron atom bonded to 3 fluorine atoms. Now, based on everything your textbook ever told you about atoms desperately needing 8 electrons, take a guess. How many electrons are surrounding that central boron atom? You'd assume it has to be exactly 8 for the molecule to even exist, right? Well, the actual number is 6. Yep, 6. Not 8, not even close. Boron is just sitting there, perfectly stable, perfectly content with exactly 6 electrons. So logically, we kind of have to conclude something right here. Either boron somehow magically broke this unbreakable octet rule, or the rule itself just isn't the whole story. And remember, BF3 isn't some weird, unstable, artificial thing cooked up in a lab. It exists everywhere in nature, and it completely ignores your textbook's rules. Okay, let's move on to a heavier element to see how this builds. Check out phosphorus pentachloride, or PCl5. If we count the electrons around that central phosphorus atom, which is bonded to 5 chlorine atoms, we get 10. Once again, the octet rule specifically and forcefully demands 8 electrons, but nature gives us 10. Phosphorus is sitting comfortably with 10 electrons around it, totally sidestepping that rigid boundary. The supposed universal law is failing all over again. Now, you might be sitting there thinking, okay, maybe heavier elements just act a bit weird, right? Maybe these are just rare exceptions to the rule. Well, let's throw out one more rapid-fire example to really put that idea to the test. Let's look at sulfur hexafluoride, SF6. 12. There are exactly 12 electrons chilling around that central sulfur atom. This perfectly illustrates that these examples, they aren't just weird, rare anomalies or little flukes of nature. They are undeniable physical proof that the octet rule, at least as it's taught in schools, is fundamentally incomplete. So if the golden rule of 8 is busted, what's actually going on down at the atomic level?
Section 2. Redefining atomic stability beyond the number 8.
The octet rule is like a traffic rule that works for most cars, but not for trucks. I absolutely love this quote. This metaphor perfectly captures what's actually happening here. It shows that different vehicles, or in our case, different atoms, play by completely different rules. Your textbook taught this concept as if the speed limit applied to literally every single thing on the road, from a tiny bicycle to a massive freight train. But in the chemical world, that's simply not the case. The real truth is that atoms seek stability. But stability absolutely positively does not always equal the number 8. For some atoms, stability means 6 electrons. For others, it means 10. And for some, like we just saw, it means 12. Different atoms read stability in entirely different ways. Time everything to the magic number 8? That's the first big lie of your chemistry education.
Section 3. The electronegativity bond illusion, when mathematical predictions fail.
If you've taken a chemistry class, you have for sure seen this table before. Let's walk through it quickly. It's the rigid mathematical formula used to predict chemical bonds. It dictates that if the electronegativity difference between two atoms is less than 0.4, the bond is purely covalent. If the difference is exactly between 0.4 and 1.7, it's polar covalent. And if it's strictly greater than 1.7, boom, it's an ionic bond. Notice how incredibly definite and absolute those brackets sound? It's taught as pure, unbreakable mathematics.
Well, let's test that mathematical rule right now using hydrogen fluoride. The electronegativity of hydrogen is 2.1 and fluorine is 4.0, which gives us a difference of exactly 1.9. According to the textbook, anything over 1.7 should be ionic, so HF should be ionic, behaving just like sodium chloride. But in reality, hydrogen fluoride is a polar covalent compound. Despite what the rigid math says, we can physically measure its covalent bond length and its bond energy. The strict formula just completely fails here.
Let's test the formula one more time with beryllium chloride. With a difference of 1.5, the textbook puts it squarely in the polar covalent bracket. But here's the reality. Beryllium chloride is purely covalent. It is absolutely not a polar covalent compound. So for a second time, the strict mathematical prediction completely fails to align with physical reality.
Section 4. Exceptions or systematic failures. The 50% reality check. Now you might be thinking, okay, sure, there are a few flaws, but aren't these just rare exceptions to an otherwise solid rule? Doesn't the rule still mostly work? Well, here is the stark reality. The supposedly universal, all-encompassing octet rule that gets entire textbook chapters dedicated to it actually works for a grand total of 7 elements. Yep, just carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. That is a staggeringly small number for a rule that's taught as a universal law of chemistry. Just compare that to the sheer volume of elements the rule fails for. Boron, beryllium, hydrogen, aluminum, silicon, phosphorus, sulfur, plus the entire transition series. We're talking about cobalt, copper, iron, nickel, zinc, chromium, manganese. The list just goes on and on. The octet rule literally fails for 50% of the periodic table. Let's really drive home the major philosophical takeaway of this whole explainer. These are not exceptions. By definition, an exception is supposed to be a rare anomaly. What we're looking at here are predictable, systematic failures. When a foundational scientific concept fails this commonly, this widely, and this predictably, well, we as focused learners can't just brush them off as mere exceptions just to keep a flawed rule alive. Which brings us to the end of our explainer. And I want to leave you with this really powerful, provocative question to think about. If a rule works perfectly for exactly 7 elements, but completely and systematically fails for 50% of the entire periodic table, is that actually a rule? Or is that just a coincidence? It really makes you rethink everything you assumed was an established scientific law, doesn't it? Keep questioning, keep learning, and hey, don't be afraid to challenge the textbook.